right, everyone. So this is chapter 16. So in this chapter, we're going to cover sound. Remember, sound is a longitudinal wave, and most of the things that we already covered in chapter 15 will be also applied to sound, but there are some things that are unique to sound, and we're going to be basically exploring in greater detail in this chapter. So, so like the highlights of this chapter, right? The units is, so we're going to study about characteristics of sound, mathematical representation of longitudinal waves, and then some applications. So how to represent sound in terms of intensity and in terms of the intensity level, we call it like decibels. Then look at the standing waves um, in terms of like, let's say sound standing waves. We're going to be using open tubes or closed tubes and look at how the same standing wave that we looked at generating on a string can also be applied to a sound waves. Then we're going to look at superposition, specifically for the sound, how you can have two sound sources and you can have a constructive and destructive interference. And then, you know, we're going to look at beats. Also, we're going to look at, interesting, let's say, application of a sound waves, which is known as a Doppler effect. Not unique to sound waves, but probably, sound wave, this Doppler effect is more visual, let's say, if you're talking about like sound waves. It can also be applied to light waves, but only if you're looking at the long distance stars and things like that. Anyways, in terms of then sound, remember, so sound is a longitudinal waves, means that the medium that generates the sound wave propagates back and forth, not perpendicular to the direction of the wave, but back and forth with respect to the direction of the wave. All right, so one important thing about sound is that it requires a medium. It's a mechanical wave, and the medium for sound is molecules. So, for example, if there is no air molecules, there is no sound. You can't hear me in the room if there are no air molecules. So that's why there's, for example, there is no such thing as sound in space, because space is vacuum. There are no molecules there. There is no sound. So you can also have sound in water. For example, actually, sound is moving much faster in water than, let's say, in air. So that means, it requires molecules, so that molecules basically vibrate back and forth and transmit the information. So generally, you can think of like, let's say you need, some kind of moving fluid, right? So moving, liquids or gas in order to propagate the sound. And it has different speeds. And here's a table for you know, the sound, speed of sound in different materials. So you can see that even in air, it, not only depends on the material, it also depends on temperature. So this is, you can think of like around room temperature, so 20 degrees Celsius. It is moving at 343 meters per second. At 0 degrees Celsius, it's moving at 331 meter per second, and so on and so forth. That means generally the speed changes with temperature, and there's this equation where we can take speed to be approximately 331, which is, at zero temperature, a 0 degree, Celsius temperature, and then plus zero point 0.6 times t meters per second. So we can technically use this equation to then referencing the speed of sound in, let's say, in air at 0 degrees Celsius, then to find the temperature or the speed at different temperatures. So you can see, right, technically this term can become positive or negative depending if you're going above the 0 degrees Celsius or below the 0 degrees Celsius. So this is basically for the uh, speed of sound. You can use this in a way for other mediums too, but we're going to pretty much concentrate on mostly looking at the speed of sound in air. So 343 meter per second is at room temperature. That's going to be mostly used for most of the applications in this chapter, unless you specifically told that there's a different temperature. go ahead and use 343. So for example, so here's one application we're going to see at the end, which is the ultrasound. So there's an image of a baby, and we use sound wave to actually generate that image. So we're going to talk about that at the end. And another thing about sound here is, for example, humans have audible range. That means we can hear the sound between 20 hertz and up to 20,000 hertz. This is known as audible, range for humans. There could be animals that can actually hear beyond that, in terms of like a way above 20,000 or way below 20 hertz. But for us, it's sort of like, let's say that. So we're going to talk about, let's say there's loudness, right? And the loudness is pretty much in terms of the pitch of a sound. So, and frequency is related to the pitch of a sound. So you can say that low frequencies are perceived as low pitch, like a bass notes, right? And high frequencies are, high pitch, like a treble notes. And sound waves, they're above 20,000 hertz is known ultrasound. So that's an ultrasound if it's greater than 20,000, so above 20,000. And then the sound that is less than 20 hertz is known infrasound. So let's say then the frequency, let's say less than 20 hertz is then infrasonic. Okay. So, and this is, for example, an image that generated with the ultrasonic at ultrasonic frequencies, let's say 50,000, 100,000 hertz, and you can generate an image of a baby, for example, that is basically you send a sound wave and it can go through the skin, but then, certain things like, it cannot go through. But most of the time, what we're going to see, what we also learned in the last chapter is that wave reflects, right? It reflects back. Even if it transmits, it always reflects parts of it, back. So that means parts of the information is always reflected back, and then we can use that to generate an image like that. All right. So one thing about this, a sound wave, we can have two different representation of that. One is in terms of how the molecules are displaced when there's a vibration. So let's say there's a speaker, and then the speaker vibrates the air molecules in front of it. That's how the sound wave propagates. So we can represent sort of like, let's say, a graph of displacement of those molecules as a function of position. That means, vertical position as a function of horizontal position. But we can also represent in terms of the pressure, in terms of, like, let's say, a region where there's a high concentration of air molecules is known as expansion. And then another region where it is known as a region where there's actually a high concentration is known as a compression. And the region where there is a low concentration is known as expansion. So generally, obviously, compression is higher pressure because you have more, air molecules, and air molecules basically, more air molecules you have, more collision, more interaction, higher pressure. Lower the concentration, well, lower pressure. So when you're doing the graph, you can do a graph of this, a pressure as a function of position, how the pressure changes. And you can see, right? So this is high, let's say the highest concentration. So you have a crest, and then low concentration, you have a trough, crest and a trough, and so on and so forth. So that's kind of like in terms of doing the graph for the pressure as a function of position. You can also look at in terms of displacement, as I mentioned, right? And one thing you will see that they are about 90-degree out of phase. So the crest and a troughs, they are not on top of one another. That means you don't have a crest of displacement versus position graph compared to the pressure versus position. They are exactly pi over 2 or 90-degree out of phase. Okay. All right. So here's then what we can do. If we are looking at to derive some kind of equation to represent how the sound wave is propagating, So very similar to the traveling wave equation that we had in the previous chapter. So we can see that generally, when we talk about, let's say, as air molecules moving, we can look at how the air molecules moving in some kind of, like, let's say, a volume of interest. So here's, for example, we start with this. So this is some kind of, you can see, right, the some kind of fluid, because again, it could be liquid or a gas. So let's say some kind of fluid that is being disturbed, and then it's basically propagating. So what we have here is L sub I represents the length, and let's say obviously you have sort of like, let's say, the area. Let me use a different color. So let's say the area of interest. So you have area and length, and let's say this is the column of you know air concentrated, like, let's say, fluid that we're considering. So let's say that's the crest, for example, and then it moves as a function of you know time and position. So one thing we have here, we have this equation where change in volume, basically change in volume over the volume, equals negative of the pressure over the B, which is the bulk modulus. So this is the equation that we have used before, where the pressure equals negative of B times delta V over V. So that's the equation for the bulk modulus. So you can basically also write it as a ratio like that. Now the idea here is this. So in terms of, as as the air column is the fluid column is moving, there is a displacement. Okay, so there's a displacement, sort of like, let's say, this amount of this delta x. Okay, so then I can write this in terms of negative b times, where delta v is change in volume. Well, I can represent change in volume in terms of, remember, the volume is, let's say in this case, will be, if you talk about area A or area S, so it will be S times some kind of, a displacement. So the delta D. Okay. So let me do it actually, delta X over here. So the delta X. And then change in volume then will be S times delta D. So then it becomes delta D over delta X, but both of them in terms of S times delta D and S times delta X. Okay, so we have basically something like this. So this is delta V and this is V. Okay, well, from here we can then cancel the delta, cancel the S, and we have then negative B delta D over delta X, and then we take the limit. So P is equals to the limit where delta X approaches 0. Then this becomes B times partial derivative of D with respect to X. And that's basically what we have over here. So negative B times partial derivative of D with respect to X. Remember, D here is the distance those molecules go back and forth, right? So basically that they're like, let's say, local displacement because of the vibration. And then the delta X is just general displacement of the wave itself, because those molecules just vibrate back and forth. And delta, this D, right? This delta D technically represents that particular local vibration. All right. So if I take then that equation, and remember displacement wave. So this is the displacement wave that we have seen in previous chapter, where D is a function of x comma t equals a amplitude sine of kx minus omega t plus phi naught, which is the phase constant. Well, what we could do in here is this was the equation for the traveling wave, and then P, a pressure wave, is basically negative b times then the derivative of that as a function of x. And remember, this is a partial derivative. That means we treat t as a constant and only take the derivative with respect to x. That means if you're doing the derivative, you first, take the derivative of the sine, so which becomes cosine. And then you take the derivative of the argument of the sine, which is kx minus omega t plus v naught. And the only term that has x is this guy over here. So then the derivative of the kx is just basically k. And that's what you have. So that's why a was already there, b was already there, and then the derivative basically gives us cosine kx minus omega t plus v naught, and then this factor of k. Okay, so that was the derivative of this guy. Then from here, we can take those three quantities together, wave number times bulk modulus times the amplitude, and we're going to call that the pressure amplitude. So the pressure amplitude, K times B times A. Okay, so that's basically the pressure amplitude. So we can replace that, a product of those three quantities as a just P max, maximum pressure, as a, amplitude of that P as a x comma t. So basically for the pressure wave. Okay. So then again, going back then replacing what the wave number is. For example, if you remember, right, the wave number is 2 pi over the wavelength. Well, 2 pi over the wavelength, where wavelength was also speed divided by the frequency. That means I can say that this is 2 pi over the speed divided by frequency, or 2 pi frequency over the speed. And then this term replacing, k over here. That's basically what the second equation does. So that means this 2 pi f over the v is nothing but the, wave number. Okay, so we replace that, and then we have the, you can see, right, it's basically amplitude depends on the frequency and the speed of sound. In a way, speed of sound basically it's a temperature dependent, but more or less we assume that to be constant if it's a room temperature. All right, and also look at the graph that we have, and also you can see that they are exactly 90 degree apart, right? There's out of sync, 90 degree, they're out of sync in terms of when this guy here is a cosine, this is then a sine. So that's always going to be in terms of this. So that's why if I move 90 degree from there to here, I'm pretty much getting that graph over there. Okay. So applying Newton's second law along x to displacement dx comma t of a small cylindrical piece of fluid basically gives us a wave equation. Okay. That means we can pretty much derive this equation over here, very similar to the way we derived the last equation in the previous chapter. So this is just in terms of that, a bulk modulus, and rho is basically the density. So again, comparing this to the general wave equation that was discussed, right, for the string that I derived in the previous chapter, we can, then rearrange and find the speed of sound equation that in terms of, let's say, bulk modulus and density. Okay, so here's another equation, right? So this is just like, let's say, speed of a string wave had a specific equation, f of t over mu. Then the speed of sound in a fluid also has a unique equation where it's a bulk modulus divided by the density. So the density of that fluid. Okay. So another thing we have is, as I mentioned, right? So the sound, when you talk about the loudness of the sound, we can represent it in technically two different ways. So we can talk about in terms of intensity of a wave, which we already have looked at also. So intensity, if you remember, is power per area. So basically, power itself is energy per unit time, then per unit area. So that's what pretty much this intensity is. Intensity is the, how much energy is basically transmitted by the wave as a function of time through some kind of, surface area A. Okay. Units, watts per square meters. That's for the intensity. And one thing we can do here is that when we talk about then sound, we can talk about sort of like, let's say, the intensity of a sound in terms of some kind of reference, let's say intensity. And the reference intensity is the what we call threshold of hearing. So this lowest one over here. And that is 1 times 10 to the negative 12. So think like this. In a way, that is the faintest sound we can hear. Okay, so we take that as a reference. So you can see, right, there are two columns. One is in terms of intensity, the other one is sound level. So we're going to get to that in a minute. But the idea here is this. In terms of what we have here is you have your reference, and then after that's basically the lowest, and then after that everything is pretty much increases. So in terms of the, you can see, right, for example, if you're comparing threshold of hearing to a whisper, and to, I don't know, like a traffic, a truck traffic, a siren, a loud rock concert, right? All of those, values start increasing because they have more energy per unit area. That means, for example, if you're using, like, let's say um, the membrane in your ear as that surface area, right, and how much sound entering your ear, then, for example, the values here as increasing also represent how much energy which enters your ear, and how, let's say, how much that affects the membrane in your ear, right? Because more, I don't know, loud the music, the sound is, more violently, let's say, the membrane is vibrating. So that's why if you go into higher and higher, let's say, a loud concert, rock concert, or threshold of pain, right? That means, and or a jet plane and things like that. Those are such high intensity, such high energy. That means, let's say the membrane in your ear start vibrating so violently that it can technically a rupture. So that's why threshold of pain. So it can be actually painful for you. All right, so, but you can see those numbers are, kind of like not very easy to work with, right? A lot of, small numbers, 10 to the negative 11, 10 to the negative 10, negative 7, 8, and so on and so forth. So then what we have here is we have another sort of, like, let's say, way of representing, you know, uh, this intensity of sound. This is in terms of the sound level in decibels. Okay, that means we can take the sound intensity in watts per square meter, and we can use it to convert it to basically a sound level, which we can see a little bit, easier to work with, because technically the same threshold of hearing is not some 1 times 10 to the negative 12, it's 0. Okay, and then after that everything is increasing, so 10, 20, 30, 40, 50, and so on and so forth. So it's a little bit easier, cleaner way of representing the sound level. Okay, so there's a very straightforward way of looking at it. It's not directly proportional or something like that, it's actually logarithmic. So the sound level measured in decibels, that's the units for the sound level, is 10 log of ratio of whatever intensity you're considering over the reference intensity, I naught. So I naught, remember, is the threshold of hearing. So we're going to take that as a reference. So that's right. For example, right, if you want to look at the, let's say, intensity, um, for example, a whisper, right, which is 1 times 10 to the negative 9. So then you can say that this is equals to 10 log 1 times 10 to the negative 9 over 1 times 10 to the negative 12. So here we get then 10 log, well, 1 times 10 to the negative 9 over 1 times 10 to the negative 12. Well, that just basically give us 10 to the 3, or 1000. Log of 1000 gives us 3, and then 10 times 3, we get 30 dB. And that's what we have here, 30 dB for the whisper, so 30 decibels. All right, so relatively straightforward, conversion. You can even go back and forth. If I give you, let's say, intensity, you should then, oh, well, if I give you dB, you should then kind of go back and solve for the intensity. All right, so one thing we also have here is, you can see, right, in increasing the sound level of 3 dB, which is doubling in intensity, is a very small change in loudness. So, I mean, that's a small enough that we're not even going to be able to tell the difference. In open areas, the intensity of sound diminishes with distance. I mean, we know that, right? So if somebody's speaking 1 meter from you, you can hear it perfectly fine. Person goes 10 meters, still fine, but 100 meters, you can barely hear. Like 1,000 meters, you can't probably hear anything. But because of, this intensity being proportional to 1 over r square, further it is, more scattering you get and energy kind of get dissipated, and you can't really hear much. So obviously then that's we're assuming that, so like an open space where the sounds technically can propagate in every direction. So that means, that energy that is generated pretty much, radiates in every direction. You can say, right, in closed space, however, this, you know, kind of, a little bit more harder to kind of keep track of because of the reflections. So that's why, for example, let's say if you're in a room, you have a speaker, you can't really find the blind spot, or like, sort of like blind spot in a way that, the sound can cancel each other. But if you're in an open space, you can actually put two speakers, which we're going to see in a little bit, two speakers such that you can find at some point where they're, the waves actually cancel each other. You get a destructive interference, and you can find the position where you hear no sound. All right, so that's kind of what we have. So this is equation for the in terms of intensity, right? It's 1 over r square. Well, simply because, remember the intensity equation is power per, area, and area generally, you know, if it's like, let's say, three-dimensional, let's say the sound is moving as a sphere, area of the sphere here is 4 pi r square. So that's why it's 1 over, 1 over r square dependence. So here what we have is intensity equation that we derived in previous chapter. Then what we're doing here is we basically including some of these new things that we just derived for the amplitude of a pressure wave. Because here we have A, the amplitude, and then I just showed you that change in pressure, right? This amplitude of the max, the pressure wave is equals to, remember, like it's K times B times A, which then can also, once you replace K with a 2 pi over wavelength, basically becomes uh, 2 pi FBA over V. So that's basically the pressure wave amplitude. And then from here, we can even write it in terms of, so 2 pi F A over V. And then remembering that, B is related technically to the velocity because square root of B over rho is equals to speed. So if I square both sides, so I get then V squared is equals to B over rho, or B is equals to V squared times rho. So then I can rewrite this in terms of 2 pi times F times A. Oh, sorry, there's a B over there. And then for the B, I'm replacing B with V squared over R. So V squared, V squared times rho divided by V. This cancels out. And then I have 2 pi F A and rho. That's what the, amplitude of the pressure wave can also be represented. Then from here, I can say that amplitude is equals to, a maximum amplitude for the pressure wave divided by 2 pi rho VF. And then replace that amplitude with this quantity squared. Okay. That means in a way what we have here then, if I'm doing that, then some of like for example, pi squared is going to cancel out. Then let's say that one of the density is going to cancel out, and then the frequency is going to cancel out, and we just have intensity equation in terms of the amplitude of the pressure wave square divided by 2 times V times the density of the fluid. Okay. So just manipulation of the equation until you get something a little bit more simpler, a little bit more, let's say, specific compared to the previous equation that we derived. Okay. So in any case, in this, it shows that the intensity is proportional to the square of the pressure wave amplitude. And one important thing to see from this equation, frequency cancels out. That means it's not proportional to frequency at all. It's independent of the frequency. All right, so this is in terms of the ear sensitivity. Let's say when you're talking about sort of like a loudness. So, and you can see, right, it varies with frequency. And these curves translate intensity into sound level at different frequency. So generally we are more or less more sensitive at this region, somewhere between 1,000 and about 5,000. And this represents in terms of sort of like a units called phones, which is sort of like a sound loudness level. And it shows that in a way, the the frequency that we see over here, right? It's pretty much not non-linear. You know, it's kind of like a logarithmic. So, and whenever you hear some kind of sound at 1,000 hertz, let's say some decibel level, right? Uh, for something else, it might be at completely different decibel for the same frequency. So, so for example, 40 or 60 or 20, if you looking at the 1,000 hertz, let's say frequency, then, you know, let's say 20 dB, for example, at 1,000. And, but if you're looking at, for example, 100 hertz instead of 1,000 hertz, same thing, actually to have the same loudness should be, for example, instead of 20, should be around like, you know, maybe about 45 or 50, or probably 50 dB. Or for example, here 40 at 1,000 hertz, the loudness that you hear for that sound at 1,000 hertz, if you have 100 hertz, then same effect will be, in order for same effect to happen, right? So same loudness, it should increase up to about 60 something dB. So that's why it's not a linear, it's kind of like a logarithmic scale, so like that. All right, so now we're ready to look at some examples here. So here's an example where a 100-watt light bulb produces a 5 watts of visible light. Remember, light is a wave, so we're not really looking at light in a greater detail because it's not a mechanical wave, but still it's a wave. We can apply most of the same thing, you know, some equations and properties as we talked about. So let's say 100-watt light bulb produces 5 watts of visible light. The other 95 watt are actually dissipated as heat and infrared radiation. That means things like this. When you purchase a 100-watt light bulb, 95% of that light bulb, right, basically is wasted. You know, it doesn't produce, you know, light. It produces, you know, heat and infrared radiation. And infrared radiation is something we can't even see. So what is the light intensity on a wall 2 meters away from the light bulb? Okay, so assuming that, you know, light, just like sound, propagates in 3 dimensions, we can look at it in terms of this. So intensity is equals to power per square area. And power is basically the effective power that we have, which is 5 watts. So 5 watts over the area. Well, area is 4 pi r square. So then 5 watts over 4 pi, well, r is the distance of, you know, 2 meters square. So we can say that it's 0.0, sorry, 0.095 watt per square meters. That's for the intensity, you know, of the light on a wall 2 meters away from the light bulb. All right, so part B, it says a krypton laser produces a cylindrical red laser beam 2 millimeters in diameter with a 5 watt of power. What is the light intensity on a wall 2 meters away from the laser? Okay, so let's see what we have over here. So this is part A and this is part B. So for part B, we are basically looking at same equation. Intensity equals power per area. But if this is, let's say, a light bulb, when it produces light, light kind of propagates in every direction, so like a sphere, spherical. But when you have a laser, laser is much more concentrated. So technically, it moves like a, there's like some kind of circular, cross-sectional area. So this becomes 5 watts over area, but for the circle, so pi r square. That means this is 5 watts divided by pi, so 2 millimeters in terms of the diameter, right? So we can use this, half of that to be a radius, so 1 millimeter. So 0.001 meters squared, that's, the cross-sectional area. So then we're going to get 1.6 times 10 to the 6 watt per square meters. And you can see, right, what a big difference. This is basically 95 milliwatt. This is about, 1.6 megawatt per square meters. Again, because it's much more concentrated, and moves with much higher intensity. So that's why let's say, the lasers are very dangerous. You don't want to point the laser towards someone's eyes and something like that, because they are, very high concentrated energy and can damage it. Okay, so here's another example. The sound intensity level 5 meters from a large power saw is 100 dB. At what distance will the sound be more tolerable? 80 dB. So now let's look at 100 dB. 100 dB, I guess apparently it's very dangerous. So we can go back to a table that I gave you. We can see, right, 100 dB, so like a siren at 30 meters. So it is, let's say not quite threshold of pain, but, kind of close. 80 is sort of like, let's say, a busy street traffic. So something that is more or less manageable, loud, but still manageable. So that's why it's asking, more tolerable 80 dB. So what we want to do here is we want to find, in terms of given the sound intensity 5 meters from a large power, so it is 100 dB, right? And we can see that there's sort of like a difference between those two of about 20 dB. Okay, that means we can say that taking 100 as beta 1 and 80 as beta 2, so we can find the difference, beta 1 minus beta 2. So 100 dB minus 80 dB, so we get 20 dB. That's a, difference in decibel level. All right, so what we'll do then is next. All right, so next what we'll do is this. So beta 1 minus beta 2 equals, so beta 1 here is 10 log I1 over I naught, and minus 10 log I2 over I naught. Okay, so remember, so this is basically 20 dB, and on the right side, so I can factor out 10, and I have log of I1 over I naught minus log of I2 over I naught, where from here, because, for example, log A minus log B, so if I have log A minus log B, this is equals to basically log A over B. So using this, I can get that as, in terms of 10 log, you can see, right? So 10 log, then I1 over I naught is my A, I2 over I naught is my B. So it becomes I1 over I naught divided by I2 over I naught. I naught cancels out. And then I have just I1 over I2. Okay. So 10 log I1 over I2. That means what I have is this. So 20 dB is equals to 10 log I1 over I2. Okay. Now next, divide both sides by 10. So then here I have 2 dB. So that means 2 dB is equals to log I1 over I2. Okay. Then from here, so basically rearrange where I end up with I1 over I2. So take basically, the power of 10, right? So then is equals to 10 square. So basically this becomes the exponent for my power of 10. So then this ratio, that means kind of like this, right? Base 10, so then I1 over I2 is equal to then 10 square, which is then equals to 100. Now that I have this, now that I have that, what that ratio is, next I can do this. Even though I'm changing the power that this is going to generate, is going to be the same, regardless if it's 100 dB or 80 dB. Intensity changes. But remember, what we're doing here, we're moving, right, at some distance d in order to change the, intensity level. But power 1 is same as power 2. And remember, intensity is power per area. So then power is intensity times area. That means power 1 is intensity 1 times area 1. Power 2 is intensity 2 times area 2. Or the ratio of I1 over I2. Right. Ratio of I1 over I2 is then equals to the ratio of A2 over A1. Okay. All right. Now, what I have here is my area 2 is 4 pi R2 square. My area 1 is 4 pi R1 square. 4 pi's cancel out. That means that, area 2 over area 1 just ends up being R2 square over R1 square. And what I have is that ratio of R2 square over R1 square is equals to the ratio of I1 over I2. But I already have I1 over R2 is just nothing but 100. This is just nothing but 100. That means from here, remember, I want to find the distance 2. That means R2. And then from here, I can just say, you know what, R2 square is equals to 100 times R1 square. Taking the square root of both sides. So my R2 then is equals to square root of 100 times R1. Well, R1 is squared, so inside the square root, so it can come out. So R1 times square root of 100. Well, square root of 100 is also just 10. Well, R1 then was 5 meters. So 5 meters times 10, we get 15 meters. That means you have to go from 5 meters to a 50 meters in order for your sound level to decrease by just 20. But it's, definitely makes a much more tolerable, let's say, sound to your ears. All right, so here's one more example. Two loudspeakers on elevated platform are at opposite ends of a field. Each broadcasts equally in all directions. The sound intensity level at the point halfway between the loudspeakers is 75 dB. What is the sound intensity level at the point 1/4 of the way from one speaker to the other along the line joining them? All right, so let's see what we have here. So you have two sound sources, and we're given that halfway between them is 75 dB, but we want to find basically a 1/4 of the way from one of them, what will be then the intensity level. So we're basically dealing with, let's say, very similar to the previous example, right? Two sources that produce same power. That means, like energy per unit time, right? Because there are two, you can think of like identical loudspeakers. So they produce, sound with the same power. So let's say here's the first one. Let's say here's the second one. And the distance between them, I don't know, let's call this D. So then halfway right here, right? So let's say taking this guy to be 0, this one to be, for example, D. This is basically D over 2. Okay. And then what we have here at that point, we have our intensity 1, which is, intensity 1, but let's say in terms of beta 1 equals 75 dB. And then we have somewhere over here, right, quarter wave. So let's call this 0.1. Let's call this 0.2. At that 0.2, then what I have here is that this distance is 1/4 of a D, and distance is 3/4 of a D, right? And then let's say beta 2 here is unknown. We want to find that, but let's say I2 and beta 2, right? So we have intensity 2 and then intensity level 2. So those are the things basically we're going to be looking for. Okay, so our goal is to find that beta 2. Okay, so is it going to be higher than beta 1 or lower than beta 1? Well, we're going to find out once we do the calculation. Again, the idea here is that we're assuming that those two speakers producing same power, and then let's say it's an open region, right? It's a, let's say a field, so there should be no reflection, so we don't have to worry about those things. So we can then use the equation for the delta beta that we kind of like looked at already. That means we can say that delta beta is beta 2 over beta 1. Okay, and same way, right? So so like let's say it's 10 log I2 over I naught minus 10 log I1 over I naught. And to kind of cut it short, remember this basically becomes 10 log I2 over I1. So A over B, right? This is A, this is B, so I2 over I1. So this one, since 2 minus 1, so then the ratio is 2 over 1, I2 over I1. All right. So now, again, power 1 is equals to power 2. Okay. Which means that basically, again, power is equals to intensity times area. This means intensity 1 times area 1 equals intensity 2 times area 2. So we can kind of look at it in terms of that. All right, so let's write down what I1 is. So I1 is equals to P over 4 pi D over 2 square plus P over 4 pi D over 2 square, which is basically, from each one, right? At that point 1, basically both speakers send a wave, and this is the intensity of both of those waves reaching at that point. So then combine those two together, we get 2p over pi d square. All right, so then looking at intensity 2, let's use this. So intensity 2. So then again, same way will be p over, so the first one here, right? travels this much. So 4 pi d over 4 square plus p over 4 pi over 3/4 of d square. Okay, so again, combining those two together, we should get 40, kind of rearranging, right? So 40p over 9 pi d squared. And then from here, I can see that my I1 was 2 pi, 2 times power over pi d squared. So that means I can rearrange this one in terms of the I1. I can say it's basically 20 over 9 times I1, right? Because I can say that this is 20 times 2, and then that's basically my intensity 1. All right, so that means writing intensity 2 in terms of intensity 1. That's because, remember, there's a ratio. We didn't have to, but it's easy. It will make it easier later on when we start canceling things. Okay, so if I come back to this equation again, delta beta is equals to then 10 log I2 over I1. Well, my I2 here is then 20 over 9 I1 divided by, well, I1. So then I can cancel the I1. That means just 10 log 20 over 9. Well, I calculate this, I'm going to get 3.48 dB. That means change in beta going from 0.1 to 0.2 is 3.48 dB. Okay. Well, this is equals to delta B. Delta B was beta 2 minus beta 1. And remember, I do have beta 1, 75. That means beta 2 is equals to 3.48 plus beta 1, which is 75 dB, right? Then what we get is 75 plus 3.48. So more or less, roughly 70, so this, let's say 78.48 dB. So that's then our answer. That means in a way it increases. So going from 75 to roughly 78.48 dB.